Welcome to the lecture series on CFD Part 1. This is lecture 19 on examples of solution of Navier-Stokes equations for steady-state flows. Some of the solution methods described in previous lectures were applied to two-dimensional test cases which are widely used for testing solution methods for the Navier-Stokes equations, lid-driven and buoyancy-driven flow in a square cavity. The aim of this lecture is to show how different choices affect the efficiency of the iterative solution process and the accuracy of the obtained solutions. 6 systematically refined uniform grids and 5 non-uniform grids are used to test the grid dependence and convergence rate toward grid-independent solution. Simple algorithm is tested with both staggered and collocated arrangements of variables on the same grids. Then the performance of simple algorithm and implicit fractional step method, or IFSM, is compared for the collocated grids. The influence of under-relaxation factors for velocities and pressure in simple and time step size, or CFL-number, in IFSM on both efficiency and accuracy is also thoroughly investigated. Another important parameter is the Rhie-Chow correction on collocated grids. Computations with IFSM were performed both with and without this correction, and the consequences are discussed in detail. Finally, the performance of two-dimensional research codes, which are available in supplementary materials, is compared with the commercial CFD software Siemens STAR-CCM+. The first test case is the lid-driven cavity flow. The flow is driven by a moving lid on top of the cavity with dimensions 1 by 1 meter. Lid velocity is constant, u lid equal 1 meter per second. Reynolds number based on lid velocity, fluid viscosity, and cavity height is equal to 1000. The top left and the top right corners are singularity points. Velocity jumps instantly from 0 at vertical walls to lid velocity of 1 meters per second at the lid. Lid motion creates one large vortex in the cavity, which is clearly visible in this plot of velocity vectors. Secondary vortexes are created at the bottom right and bottom left corners. These are very weak and cannot be clearly seen in the vector plot. The moving lid attracts fluid to the top left corner. It then follows the lid motion due to the no-slip boundary condition. The downstream vertical wall deflects the fluid downward. At the upstream singular point, pressure tends to minus infinity because the lid is pulling fluid away from the corner, thus creating under pressure. At the downstream singular point, pressure tends to plus infinity because the lid is pushing fluid into the corner and against a fixed wall, thus creating overpressure. Singular points cause no problems in finite volume methods when midpoint rule is used for integral approximation because variable values and gradients are only needed at self-phase centers. Thus, the fact that the values are not defined at the corners is of no concern. If Simpson rule is used for integral approximation, then corner values are needed and this requires special treatment. In an experiment, a finite gap must be present between moving lid and fixed side walls. Without a gap, an infinite force would be needed to pull the lid. Because singularities affect the flow only near corners, we can ignore the gap in simulations. The effects of gap width have been studied by me and Professor Street, and these results will be published soon. They confirm that with reducing the gap width, the solution converges toward the solution with a zero gap. A series of 6 uniform grids from 20 by 20 control volumes to 640 by 640 control volumes, and another series of 5 non-uniform grids from 20 by 20 through 320 by 320 control volumes we used. Plots of both grid types with 80 by 80 cells are shown here. The non-uniform grids expand from each wall toward the center. The expansion factor for the 20 by 20 control volumes grid was 1.25. On the next finer grid, the expansion factor is equal to the square root of the factor on the next coarser grid, so that one coarse grid cell contains 4 finer grid cells. On the grid with 320 by 320 cells, the expansion factor was 1.014044. These plots show the force on lid, the force on bottom wall, and the discretization error for the force on bottom wall estimated using Richardson extrapolation, as explained in slides 14 and 15 of lecture 6. Computations were performed using non-uniform grids. The force on lid does not converge with grid refinement. It tends towards infinity, as can be seen from this plot. The force on bottom wall is converging with second order toward a grid-independent solution. A reduction of the average cell size by 1 order of magnitude leads to the reduction of the error by 2 orders of magnitude. The error on the finest grid with 320 by 320 control volumes is around 0.1%. Results were obtained using 2D code with simple algorithm and central difference approximations for both convection and diffusion fluxes. These approximations are used in all computations unless otherwise stated. These plots show the results of grid-dependent study using simple algorithm and a staggered arrangement of variables on non-uniform grids. See slide 6. The plot on the left shows the comparison of U velocity profiles along a vertical center line computed on all 5 grids. The maximum negative value in the bottom part of the cavity reaches almost 40% of the lead velocity. The plot on the right shows V velocity profiles along horizontal center line computed on all 5 grids. The negative values on the downstream side amount to over 50% of the lead velocity. Profiles of both velocities vary almost linearly in the central part of the cavity, which justifies using coarser grid in this zone than near walls, where variation in velocity is nonlinear. From the third grid onward, the profiles can be hardly distinguished from each other in these plots. A second-order convergence toward a grid-independent solution is obvious because the distance between lines is reducing by a factor of 4 from coarser to finer grids. These plots show the results of grid-dependent study using simple algorithm and a collocated arrangement of variables on non-uniform grids. See slide 6. The plot on the left shows the comparison of U velocity profiles along vertical center line computed on all 5 grids. The plot on the right shows V velocity profiles along horizontal center line computed on all 5 grids. Results on the 2 coarsest grids are less accurate than when a staggered arrangement of variables is used. See the preceding slide. From the third grid onwards, the profiles can be hardly distinguished from each other in these plots. A second-order convergence toward a grid-independent solution is obvious because the distance between lines reduces by a factor of 4 from coarser to finer grids. These plots show the comparison of centerline velocity profiles computed on the non-uniform grid with 80 by 80 cells using simple algorithm and either staggered or collocated arrangement of variables. The lines in these plots can be hardly distinguished from each other. This is also true for all finer grids. Only on coarser grids were the results obtained with a staggered arrangement slightly more accurate. It is always useful to look at some integral quantities when judging the grid dependence of numerical solutions. For the lead-driven cavity flow, the maximum value of stream function in a vortex is a suitable integral quantity. We are not solving for stream function, but because the flow rate between 2 streamlines is constant, we could compute stream function values by using volume fluxes through cell faces. Here we set the stream function value at the bottom left cavity corner to 0 and compute the values at each inner cell corner by adding to the value at the neighbor corner the volume flux through face connecting 2 corners. Positive values result for counterclockwise motion and negative values for clockwise motion. The plot on the right shows the variation of minimum stream function value corresponding to the strength of the primary vortex as the grid is refined. Results from computations with both variable arrangements converge toward the same value, but we see that on coarser grids the staggered arrangement leads to a higher accuracy. The plot on the left shows the results for the strength of the secondary vortex. Here the values are reducing with grid refinement in the case of a staggered arrangement, while they are increasing in the case of a collocated arrangement. The results are in both cases converging toward the same grid-independent value. Errors are significant on the two coarser grids. From 80 by 80 grid onward, the errors are very small. This plot shows the comparison of the number of auto iterations required to reduce the residual levels below 10 to minus 5 using simple algorithm with collocated and staggered variable arrangements for different combinations of under-relaxation factors for velocity, alpha u, and pressure, alpha p, and the 80 by 80 cells non-uniform grid. For a given value of the under-relaxation factor for velocity, there is a range of usable under-relaxation factors for pressure leading to the same performance. At both ends of this range, iterations diverge if the under-relaxation factor for pressure is further increased or decreased. For higher values of alpha u, the range of usable values of alpha p becomes narrower. The relation alpha p equal 1 minus alpha u, derived in slide 13 of lecture 18, leads to optimal performance, except for the values of alpha u above 0.9, where slightly higher values of alpha p than the value resulting from the above relation leads to a slightly faster convergence. This plot shows the comparison of the number of auto iterations required to reduce the residual level below 10 to minus 5 using simple algorithm with collocated and staggered variable arrangements for different values of under-relaxation factors for velocity, alpha u, and an optimal under-relaxation factor for pressure, alpha p. The performance is practically the same for both variable arrangements, except for under-relaxation factors alpha u larger than 0.92, where the collocated arrangement is slightly more efficient. These plots show the comparison of velocity profiles computed on the 80 by 80 control volumes non-uniform and uniform grid with a collocated arrangement of variables and simple algorithm. U velocity along vertical center line on the left and V velocity along horizontal center line on the right. The solution from the non-uniform grid is slightly more accurate because the grid spacing is smaller near walls where the variation of variables is nonlinear. These plots show the comparison of the strength of secondary and primary vortex computed on non-uniform and uniform grids using simple and IFSM algorithms with a collocated variable arrangement. On uniform grids, the results from both algorithms are similar except on very coarse grids. However, on non-uniform grids, the differences are large except on very fine grids. For the secondary vortex, its strength is overestimated on uniform grids and underestimated on non-uniform grids, but the results from both grids converge to the same grid-independent value. For the primary vortex, the results from simple algorithm are more accurate on non-uniform than on uniform grids, with the same number of cells. But with IFSM, the opposite is true, except on the two finest grids. This required an investigation into the cause of this behavior. These plots show the estimated discretization errors for the strength of secondary and primary vortex computed on non-uniform and uniform grids using simple and IFSM algorithms. On uniform grids, the errors follow the expected trend for second-order methods. But on non-uniform grids, the variation of errors is irregular, especially for IFSM. In these computations, pressure gradients in Rhie-Chow correction term are averaged. It was assumed that the cause of this irregularity has something to do with Rhie-Chow correction, and its effects were closely investigated. First, the effects of pressure gradient interpolation in the Rhie-Chow correction are investigated. This correction was described in slide 22 of lecture 18 for the simple algorithm. It has the same form in IFSM, only the multiplier in front of the square brackets is different. On collocated grids, velocities at cell faces which are needed to compute the mass flux are first computed by using linear interpolation. This is a second-order approximation as shown in slide 13 of lecture 7. Because pressure gradients at cell centers are not sensitive to checkerboard oscillations, the interpolated velocities are corrected by replacing interpolated gradient with the gradient computed at the cell face. When the grid is non-uniform, the central difference approximation of pressure gradient at the cell face, pressure at the neighbor cell minus pressure at cell center divided by distance, is second order accurate midway between two cell centers, not at the cell face. This is why literature suggests the pressure gradients are averaged rather than linearly interpolated, so that both approximations are consistent. In SIMPLE, no big difference is observed when the interpolation method is changed. However, in IFSM, averaging the pressure gradient leads to large errors and irregular behavior. When pressure gradient is linearly interpolated, as highlighted here, the results are much better, as can be seen in these two plots from the variation of vortex strength for both primary and secondary vortex. Now the results from non-uniform grids are consistently more accurate than the results from uniform grids, and the difference between SIMPLE and IFSM is much smaller than in slide 15. These plots show the estimated discretization errors for the strength of secondary and primary vortex computed on non-uniform and uniform grids using SIMPLE and IFSM algorithms and linear interpolation of pressure gradients in the Rhie-Chow correction term. The variation of errors is now closer to the expected second-order convergence also on non-uniform grids. The errors are consistently smaller on non-uniform grids. Errors in the strength of primary vortex are slightly smaller for SIMPLE than for IFSM. These plots show the comparison of U velocity profiles computed on two non-uniform grids with a collocated arrangement of variables and IFSM algorithm using two different interpolation methods for pressure gradient in the Rhie-Chow correction term. The solution with linear interpolation is more accurate than when gradients are averaged. The difference is larger on coarse grids and becomes smaller as the grid is refined. These plots show the comparison of V velocity profiles computed on two non-uniform grids with a collocated arrangement of variables and IFSM algorithm using two different interpolation methods for pressure gradients in the Rhie-Chow correction term. The solution with linear interpolation is more accurate than the solution gradients are averaged. The difference is large on coarse grids and becomes smaller as the grid is refined. One may ask, do we need the Rhie-Chow correction at all? It was invented to correct the effects of possible checkerboard oscillations in pressure, but how likely is it that such oscillations develop in the iterative solution process? Indeed, one can solve the Navier-Stokes equations on collocated grids using IFSM without the Rhie-Chow correction. Only the convergence is slow if time step is large. These plots show the comparison of centerline velocity profiles computed on the 40 by 40 cells non-uniform grid with a collocated arrangement of variables and IFSM algorithm without Rhie-Chow correction term, using two time steps differing by a factor 100. The reference CFL-number is defined with lead velocity and the average cell width as if the grid was uniform. The solutions are identical. There is no dependence on time step size. These plots show the comparison of the strength of secondary and primary vortex computed on non-uniform grids using SIMPLE with Rhie-Chow correction and two versions of IFSM algorithm. All methods converge to the same solution, but the highest accuracy is obtained with IFSM without Rhie-Chow correction. The effect of Rhie-Chow term on IFSM is much larger than on SIMPLE. The results for IFSM with Rhie-Chow correction were obtained using averaging of pressure gradients in this correction. Results are better when linear interpolation is used. See slide 17. Note that on the grid with 80 by 80 cells and finer, the results from IFSM without Rhie-Chow correction and SIMPLE are almost indistinguishable. When the grid is coarse, the time step size has a surprisingly strong influence on the solution. It becomes more diffusive as if a lower order convection scheme was used. These plots show the comparison of centerline velocity profiles computed on the 40 by 40 control volumes non-uniform grid with a collocated arrangement of variables and IFSM algorithm with Rhie-Chow correction term, using 2 time steps differing by a factor 100. The solutions differ significantly. There is a strong influence of time step size on the solution. When the grid is sufficiently fine, the time step size has a very small influence on the solution. These plots show the comparison of centerline velocity profiles computed on the 160 by 160 cells non-uniform grid with a collocated arrangement of variables and IFSM algorithm with Rhie-Chow correction term using 2 time steps differing by a factor 100. The red and the black line can barely be distinguished in these plots, confirming a negligible effect of the time step size on the solution. One of the advantages of IFSM over simple, in addition to the fact that it does not require under-relaxation, is that convergence to steady state is not as strongly dependent on the time step size as it is on under-relaxation factors in simple. This is elaborated in detail in the next slide. In simple algorithm, 2 under-relaxation factors are used, one for velocities and one for pressure. We have seen how one can choose the optimum under-relaxation factor for pressure for a given under-relaxation factor for velocities. The problem in simple is that the optimal value of under-relaxation factor for velocity is problem dependent, and therefore in most commercial CFD software the default values are rather conservative, between 0.7 and 0.8. The plot on the left shows the number of auto iterations required to reduce the residual norm, here the sum of absolute residuals over all cells below 10 to minus 5, as a function of the under-relaxation factor for velocity, alpha u, in simple for all non-uniform grids used. We see that as the grid gets finer, the increase in the required number of iterations with departure from optimum becomes more rapid. For the 80 by 80 cells grid with alpha u equal 0.8, we need approximately twice as many iterations as at the optimum value of alpha u equal 0.95. But for grid with 320 by 320 cells, we need with alpha u equal 0.8 approximately 7 times more iterations than with the optimum value with alpha u equal 0.99. With IFSM, the number of required iterations increases moderately over a wider range of time steps or average CFL numbers, as can be seen in the plot on the right. Except for the coarsest grid, the number of required iterations, which is equal to the number of time steps, because for steady state flows only 1 auto iteration per time step is performed, roughly doubles between CFL-20, which appears to be the optimum on all grids, and CFL-200. In addition to 2D codes which are available in source form in supplementary material, the commercial CFD software Simcenter STAR-CCM Plus from Siemens was also tested using the same 5 non-uniform grids. These plots show the comparison of velocity profiles computed on all 5 grids, u velocity along vertical center line and v velocity along horizontal center line. From the 3rd grid onward, the profiles can be hardly distinguished from each other. A second-order convergence toward a grid-independent solution is obvious. The results are almost identical to those from 2D code. See slide 9. Simple algorithm is used in both cases, but in Simcenter STAR-CCM Plus, convection fluxes are discretized using second-order upwind scheme, while in the 2D codes, central difference approximation, that is linear interpolation, was used in all cases. These plots show the comparison of velocity profiles computed on the 160 by 160 cells non-uniform grid with 3 different convection schemes in Simcenter STAR-CCM Plus software. U velocity along vertical center line and V velocity along horizontal center line. The results from first order upwind scheme, shown here with black line, are similar to the results from the second order scheme on the 20 by 20 cells grid, see previous slide. There is no difference between solutions obtained using muscle and second order upwind scheme. The first order upwind scheme is obviously over-diffusive. To reach the accuracy of the second order scheme on the 160 by 160 cells grid, one would need with the first order upwind scheme about 10 times more cells in each direction. These plots show the comparison of velocity vectors computed on the 160 by 160 cells grid with 3 different codes using second-order discretization: u velocity along vertical center line and v velocity along horizontal center line. The results obtained using 2D code with either SIMPLE or IFSM algorithm and the results obtained with Siemens STAR-CCM plus software are practically indistinguishable. This slide is about computational efficiency. The first table shows the numbers of outer iterations required to reduce the residual norm below 10 to minus 5 on different non-uniform grids using different solution methods. CFL is computed with lead velocity and average grid spacing, and for computations with IFSM, it was held constant at CFL equal 20. For simple algorithm in both 2D code and Simcenter STAR-CCM plus, the under-relaxation factors were set to 0.9 for velocity and 0.2 for pressure. The increase in required iterations with grid refinement is slower in IFSM than in simple. The second table shows the numbers of iterations required to reduce the residual norm below 10 to minus 5 on the 40 by 40 cells non-uniform grid using IFSM method with and without Rhie-Chow correction. CFL is computed with lead velocity and average grid spacing. At lower values of CFL, both versions require a similar number of iterations to converge. With increasing CFL, the version with Rhie-Chow correction becomes more efficient, but the solution becomes more diffusive. See slide 23. However, on finer grids, the accuracy of solutions is less affected by the Rhie-Chow correction, as shown in slide 23. This slide introduces the second test case, buoyancy-driven cavity flow. The plot on the right shows the geometry, the boundary conditions, and the temperature distribution in the cavity. The flow is driven by density variation caused by temperature variation. The hot and cold wall are held at constant temperature, TH equal 320 Kelvin and TC equal 310 Kelvin respectively. Top and bottom walls are adiabatic, that is perfectly insulated. The cavity size is 0.1 by 0.1 meter. The fluid is air, which is treated as an ideal gas. Fluid viscosity, specific heat, and thermal conductivity are assumed constant. Nu is equal to 1.8 10 to minus 5, Cp is 1003.62, and lambda is equal to 0.026, respectively. SI units are used throughout. The Rayleigh number for given geometry, fluid properties, and boundary conditions is 8.3215 times 10 to 5. See slide 17 of lecture 3 for the definition of Rayleigh number. In 2D research code, Bussinesq approximation is used. In Simcenter STAR-CCM plus, density is variable in all terms. Non-uniform grids are used. See slide 6. This slide is about the features of the buoyancy-driven cavity flow in this test case. The plots in the first row show temperature, density, and velocity vectors computed using Simcenter STAR-CCM plus software on the 80 by 80 cells non-uniform grid. The bottom right plot shows pressure distribution in the cavity. Density is proportional to temperature, therefore the variations are analogous. Warm fluid is lighter and rises up the hot wall, as can be seen from the plot of velocity vectors. The top wall deflects the fluid toward the cold wall. Note that the isotherms are orthogonal to the adiabatic walls as required. Adiabatic means zero heat flux, and this means zero gradient of temperature in wall normal direction. As the fluid gets colder, it falls down the cold wall and is deflected by the bottom wall toward the hot wall. Pressure varies very little in horizontal direction. The variation in vertical direction is due to gravity. The pressure difference between top and bottom wall is roughly equal to rho GH, where h is the cavity height and g is gravitational constant. In this test case, we are solving one additional equation for thermal energy conservation. Simple algorithm requires also an under-relaxation factor for temperature. Finding the optimum combination of under-relaxation factors for velocities, temperature, and pressure is more complicated than in the previous test case, where only the Navier-Stokes equations were solved. It turns out that the best performance is obtained when the under-relaxation factor for temperature is set to the maximum value possible. With 2D code, 1.0 was possible. Buoyancy approximation was used, while with Simcenter STAR-CCM plus, iteration did not converge for values above 0.98. Note the default values of under-relaxation factors in commercial codes are much lower. The plot on the left shows residual history from the computation with Simcenter STAR-CCM plus, and the plot on the right shows the same information for the 2D code using simple algorithm. The under-relaxation factors for temperature were set to the maximum possible value, while the factors for velocity and pressure were set to 0.9 and 0.1 respectively. The residuals are neither defined nor normalized in exactly the same way in the two codes, but the visual inspection reveals that convergence properties are similar in both codes. Residuals were reduced 9 orders of magnitude for demonstration purposes. Sufficient accuracy is achieved when a reduction by 4 to 5 orders of magnitude is obtained. These plots show the convergence of vertical velocity component, temperature, and pressure at the monitoring location, which was at I equal 5, j equal 5, or x equal y equal 1.3 millimeters, without iterations. After 100 iterations, the changes are not visible in these plots. As indicated in the previous slide, computations can be stopped after 120 to 150 iterations. These plots confirm that there are no significant variations in variable values beyond that state. This slide is about the effect of under-relaxation and time step size on convergence to steady state. The first table shows the numbers of out iterations required to reduce the residual norm below 10 to minus 6 on the 80 by 80 cells non-uniform grid with Simcenter STAR-CCM plus software. When the under-relaxation factor for temperature is held at 0.95, the number of required iterations increases as the under-relaxation factor for velocity is reduced, from 294 at 0.95 to 637 at 0.7. Increasing the under-relaxation factor for temperature from 0.95 to 0.98 leads to a reduction of required number of iterations at the same under-relaxation factor for velocity from 388 to 205. The 2D code with simple algorithm behaves similarly, but increase in required number of iterations with reducing under-relaxation factor for velocity is more moderate. Increasing the under-relaxation factors for temperature from 0.95 to 1.0 leads to a reduction of required number of iterations at the same under-relaxation for velocities from 352 to 126. 2D code with IFSM requires no under-relaxation. The time step remains the only adjustable parameter. In this case, the number of required iterations is increasing more rapidly than in the previous test case. The average CFL number around 10 seems to be optimum. This slide is about the effects of grid fineness on convergence to steady state. The left table shows the numbers of out iterations required to reduce the residual norm below 10 to minus 6 on all 5 non-uniform grids with 2D code using simple algorithm and under-relaxation factors for velocities at temperature set to 0.95. Shown is also the computed heat flux through the hot wall. The flux through the cold wall is the same within the convergence tolerance. The right table shows the same information when IFSM is used instead of simple, with the addition of time step size. Time step is halved each time the grid is refined to keep the CFL numbers the same. With both methods, the number of required iterations to reach the convergence criterion increases over proportionally as the grid is refined. The increase is slower in IFSM than in simple, as was the case in the previous test case. The computed total heat flux through the hot wall differs between simple and IFSM on the 80 by 80 grid by 0.022%. The difference in computed total heat flux through the hot wall between grids 80 by 80 and 320 by 320 is only 0.074%, which confirms low discretization errors. The plot on the left shows the variation of the computed local heat flux along the hot wall for all 5 grids when 2D code with simple algorithm is used. Only at the bottom left corner of the cavity, where the cold fluid first meets the hot wall, the 2 coarsest grids overpredict the local heat transfer rate. Elsewhere, and for all finer grids than 80 by 80 cells, the lines fall practically on top of each other, indicating low grid dependence of solutions. The plot on the right shows the comparison of solutions from 2D code and Simcenter STAR-CCM Plus on the 80 by 80 cells grid. Both codes produce nearly identical result on the same grid, which again confirms the high accuracy of solutions. These plots show the variation of velocity component V along the horizontal cavity center line for all grids, computed using 2D code with simple algorithm and IFSM. The grid dependence of computed profiles is very low. The results from the 3 finest grids cannot be distinguished from each other. On the coarsest grid, simple is slightly more accurate than IFSM. These plots show the variation of temperature along the horizontal center line for all grids, computed using 2D codes with simple algorithm and with IFSM. The grid dependence of computed profiles is very low. The results from the 4 finest grids cannot be distinguished from each other. On the coarsest grid, simple is slightly more accurate than IFSM. These plots show the variation of velocity component V on the left and temperature on the right along the horizontal cavity center line, computed on the non-uniform grid with 80 by 80 cells using 3 different codes. The results from the 3 codes cannot be distinguished from each other. This is a summary of findings from the 2 application test cases. The performance of simple algorithm is almost identical on both staggered and collocated grids. The numbers of outer iterations to reach the convergence criterion, the effects of under-relaxation factors for velocities and pressure, the effects of grid fineness, etc. are practically the same. The highest efficiency with simple is obtained in a very narrow range of under-relaxation factors for velocities, 0.95 to 0.99. The number of required outer iterations away from optimum increases faster on finer grids. Default values of under-relaxation parameters in commercial CFD software are rather conservative, 0.7 to 0.8 for velocities, and require 5 to 10 times more iterations than at optimum values. The implicit fractional step method, IFSM, does not require under-relaxation. The only parameter is the time step size, or CFL-number. Optimal convergence is obtained with CFL around 10 when Rhie-Chow correction is used, and with circa 10 times smaller values without Rhie-Chow correction. The number of required iterations is not far from optimum within a wide range of CFL numbers when Rhie-Chow correction is used, 10 to 150. The interpolation method for pressure gradients in Rhie-Chow correction affects the accuracy of results, significantly more when IFSM is used than with simple. Linear interpolation leads to higher accuracy than averaging, which is argued in literature to be more appropriate. The time step size affects the accuracy of solutions obtained with IFSM and Rhie-Chow correction. The effect is high on coarse grids. The accuracy deteriorates as the time step size is increased. On fine grids, the effect is rather low or negligible. The highest accuracy of solutions on a given grid is obtained with IFSM without Rhie-Chow correction. A disadvantage is a narrow range of CFL numbers with best convergence. Results obtained with 2D codes and either IFSM or simple algorithm cannot be distinguished from the results obtained with Simcenter STAR-CCM Plus software when the same grid is used with 80 by 80 cells or more.